January 24th, 1961, 12:35 a.m. Deep inside a classified laboratory at Sandia National Laboratories, nuclear engineer Parker F. Jones stared at technical diagrams that should have been routine safety analysis, standard procedure after any nuclear accident. Two Mark 39 hydrogen bombs, each carrying 3.8 megatons of destructive power, had fallen from a breaking B-52 over Goldsboro, North Carolina. 260 times more powerful than Hiroshima. Air Force officials assured the public there was no danger. The bombs were unarmed. Case closed. But Jones discovered something that made his hands shake as he wrote his classified report. 7 of 8 safety mechanisms had failed on impact. Only one single switch, requiring just 28 volts to operate, had prevented nuclear detonation. A switch that Sandia's own test showed had malfunctioned 30 times before. Had that device failed, lethal fallout would have reached Washington, Baltimore, Philadelphia, and New York City. 28,000 people killed instantly. Jones titled his report Goldsboro Revisited, or How I Learned to Mistrust the H-Bomb. His superiors called it a mistake. His analysis was wrong. The weapons were safe. But one engineer's willingness to challenge the official narrative would expose flaws so fundamental they would force a complete revolution in nuclear safety. If you value documented history that changes everything, make sure to subscribe. Comment your city. We want to know where these forgotten stories reach. At 23 minutes past midnight on January 24th, 1961, Major Walter Scott Tulloch felt his B-52 Stratofortress shudder violently as the right wing began separating from the fuselage. The aircraft call sign Keep 19 had been flying a routine airborne alert mission as part of Strategic Air Command's Chrome Dome operation, 24-hour nuclear patrols designed to keep American bombers constantly airborne during the height of the Cold War. In the bomb bay, 2 Mark 39 thermonuclear weapons hung from their release mechanisms, each containing 3.8 megatons of destructive power. Tulloch had flown these missions dozens of times before. The B-52 carried enough fuel for 24 hours of flight, allowing it to reach Soviet targets if the order came through encrypted radio channels. Tonight's route took them along the eastern seaboard, a familiar pattern that kept nuclear-armed aircraft within striking distance of their assigned targets, while maintaining the constant readiness that Strategic Air Command demanded. The crew of 8 had settled into the routine of long-range flight, monitoring instruments, checking communications equipment, and maintaining the precise navigation required for nuclear missions. The structural failure began without warning. At 9,000 feet above Faro, North Carolina, the aircraft's right wing started breaking away from the main fuselage. Tulloch immediately recognized the catastrophic nature of the emergency. Unlike conventional aircraft accidents, a nuclear-armed bomber breaking apart presented unique dangers. The Mark 39 weapons weren't simply cargo. They were complex nuclear devices designed to arm themselves during specific flight conditions. Each Mark 39 weighed approximately 10,000 pounds and measured 12 feet in length. The weapons featured multiple safety systems designed to prevent accidental detonation, but these systems had been engineered primarily for normal operational conditions. An aircraft breaking apart at 9,000 feet created exactly the kind of emergency scenario that weapons designers had struggled to anticipate. The bombs would experience the acceleration, altitude changes, and electrical disruptions that could potentially trigger their arming sequences. Tulloch ordered his crew to eject. 5 of the 8 crew members successfully activated their ejection seats and parachuted to safety. Sergeant Francis Roger Mattingly and Major Eugene Holcomb remained with the aircraft as it continued breaking apart, their ejection seats failing to function properly. The B-52 entered an uncontrolled descent, its structural integrity completely compromised. As the aircraft disintegrated, both nuclear weapons separated from their mounting points in the bomb bay. The first weapon, later designated the Faro bomb by investigators, deployed its parachute system automatically as it fell. The parachute deployment was triggered by a barometric switch designed to activate at predetermined altitudes during normal weapons delivery. The second weapon, which would become known as the farmland bomb, fell in free fall without parachute deployment, accelerating toward the ground at near supersonic speeds. The Pharaoh bomb descended slowly under its deployed parachute, landing in a relatively intact condition in a wooded area near the small community of Faro. The parachute system had functioned exactly as designed, allowing the weapon to reach the ground without the violent impact that could trigger additional arming mechanisms. Local residents reported seeing the parachute descending through the pre-dawn darkness, initially assuming they were witnessing a crew member's emergency evacuation. The farmland bomb struck the ground with tremendous force in a tobacco field owned by Calvin Bollinger. The impact drove the weapon deep into the soft, recently plowed earth, burying most of its 12-foot length underground. The force of impact was sufficient to trigger several of the weapon's internal mechanisms, systems designed to activate during the final phases of nuclear weapons delivery. Unlike the parachute-deployed weapon, this bomb experienced exactly the kind of violent deceleration that its arming systems interpreted as intentional deployment. Emergency response teams arrived within hours of the crash. The Air Force immediately secured both impact sites and began recovery operations. The parachute-deployed weapon was relatively easy to locate and recover, requiring standard explosive ordnance disposal procedures to render it safe. Teams from the Atomic Energy Commission, Sandia National Laboratories, and Los Alamos Scientific Laboratory were dispatched to North Carolina to assess the weapons and determine what safety systems had functioned properly during the accident. The farmland bomb presented greater challenges. Its deep burial required extensive excavation, and recovery teams discovered that the weapon had suffered significant structural damage from impact. More concerning was the evidence that several of the bomb's internal systems had activated during the fall and impact sequence. The weapon's arming mechanisms had responded to the emergency conditions in ways that weapons designers had not fully anticipated. Initial assessments from Air Force officials emphasized that both weapons had remained in safe condition throughout the accident. Public statements stressed that the bombs were unarmed and had never presented any danger to the surrounding population. These reassurances followed standard military protocol for nuclear accidents, minimized public concern while conducting thorough technical investigations away from public scrutiny. The official narrative satisfied immediate concerns. North Carolina residents worried primarily about aircraft debris in their fields and the environmental impact of aviation fuel. The broader American public, if they learned of the incident at all, received reassurances that American nuclear safety systems had functioned exactly as designed. The Mark 39 weapons had proven their reliability even under emergency conditions that exceeded normal operational parameters. 8 years after the Goldsboro accident, Parker F. Jones sat in his office at Sandia National Laboratories, reviewing technical documentation that had accumulated since 1961. As supervisor of the Nuclear Weapons Safety Department, Jones specialized in failure analysis, the systematic examination of how weapon systems behaved under conditions that exceeded their design parameters. His methodical approach to engineering problems had earned respect from colleagues who valued precision over optimistic assessments. The Goldsboro incident had been officially closed since 1961, but Jones had obtained permission to conduct a comprehensive review of the technical data. His analysis would focus on the specific behavior of the Mark 39 weapons during the B-52 breakup, examining each safety mechanism's performance under emergency conditions. Jones approached the review with the same systematic methodology he applied to all failure analyses, treating the weapons as complex mechanical systems rather than abstract strategic assets. Jones began by examining the technical specifications of the Mark 39 Mod 2 weapons that had fallen over North Carolina. Each weapon featured multiple safety systems designed to prevent accidental nuclear detonation. The primary safety mechanism was the MC-722 Ready Safe switch, an electrically operated device that controlled the weapon's arming sequence. This switch required 28 volts of direct current applied for 3 continuous seconds to activate, rotating an internal mechanism that enabled the weapon's nuclear firing circuits. The weapon also incorporated environmental sensing systems designed to detect the physical conditions associated with intentional nuclear delivery. These sensors monitored altitude, acceleration, and other flight parameters to ensure that arming sequences occurred only during legitimate combat operations. Additionally, the weapon featured mechanical barriers that physically blocked access to critical nuclear components until specific conditions were met. Jones's analysis focused on the sequence of events that occurred as each weapon separated from the disintegrating B-52. The farmland bomb had experienced violent deceleration upon ground impact, while the Pharaoh bomb had descended more gradually under parachute. Both weapons had been subjected to electrical disruptions as the aircraft's power systems failed during structural breakup. The critical discovery emerged from Jones's examination of the Pharaoh bomb's internal mechanisms. Post-accident inspection had revealed that 3 of the weapon's 4 primary safety systems had failed during the descent and landing sequence. The altitude sensing switch had activated as the weapon fell through its predetermined arming altitude. The acceleration sensor had triggered due to the parachute deployment sequence. The electrical arming system had received power from the weapon's internal battery as the aircraft's electrical systems failed. Only the MC-722 ready-safe switch had remained in the safe position, preventing the weapon's nuclear detonation. Jones discovered that this switch had been observed to activate inadvertently during previous incidents when stray electrical current was applied to its control circuits. Sandia's own testing records documented more than 30 instances where the switch had operated without deliberate activation. Jones calculated the potential consequences of nuclear detonation over Goldsboro. A 3.8 megaton surface burst would have created a fireball with a radius of approximately 2 miles, instantly killing everyone within that zone. The thermal radiation would have caused third-degree burns at distances up to 8 miles from ground zero. Most significantly, the radioactive fallout would have been carried by prevailing winds toward major population centers along the eastern seaboard. Using meteorological data from January 24, 1961, Jones determined that radioactive contamination would have reached Washington, D.C., Baltimore, Philadelphia, and potentially New York City within 24 hours of detonation. The fallout pattern would have followed the typical northeast trajectory of winter storm systems, depositing lethal levels of radiation across some of the most densely populated areas in the United States. Jones estimated that immediate deaths from the nuclear detonation would have exceeded 28,000 people based on 1961 population density data for the affected regions. Long-term casualties from radiation exposure would have been significantly higher, potentially reaching hundreds of thousands as contaminated areas became uninhabitable for decades. The technical analysis revealed fundamental flaws in the assumptions underlying American nuclear safety protocols. The Mark 39 weapons had been designed with safety systems appropriate for normal operational conditions, but the Goldsboro accident had created exactly the kind of cascading failures that weapons designers had not adequately considered. The aircraft breakup had simultaneously triggered multiple arming mechanisms while disrupting the electrical systems that controlled safety devices. Jones documented his findings in a classified report titled Goldsboro Revisited, or How I Learned to Mistrust the H-Bomb, a deliberate reference to Stanley Kubrick's film Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. The title reflected Jones's growing conviction that official assessments of nuclear weapons safety were dangerously optimistic. The report concluded that the Mark 39 Mod 2 weapons did not possess adequate safety systems for airborne alert operations. Jones recommended immediate modifications to prevent similar near accidents in the future. His analysis directly contradicted 8 years of official statements that had assured both government officials and the American public that the Goldsboro weapons had remained completely safe throughout the accident sequence. Jones submitted his report through normal channels to the Atomic Energy Commission and Department of Defense. The document immediately acquired a high classification level and was distributed only to officials with specific authorization to access nuclear safety information. The report's circulation was deliberately limited to prevent widespread awareness of the safety deficiencies it documented. The technical conclusions reached by Jones represented a fundamental challenge to the nuclear safety establishment's confidence in existing weapon systems. His analysis suggested that America's nuclear arsenal was significantly more vulnerable to accidental detonation than anyone had previously acknowledged, raising questions about the safety of hundreds of similar weapons deployed worldwide. The MC-722 ready-safe switch that had prevented nuclear detonation over Goldsboro represented a critical vulnerability in American nuclear weapons design. Jones's investigation revealed that this electrically operated solenoid switch required only 28 volts of direct current and 3 amperes of electrical flow applied for 3 continuous seconds to rotate from safe to armed position. The switch's low voltage requirement meant that relatively minor electrical disruptions could potentially trigger its activation during aircraft emergencies. Sandia National Laboratories maintained detailed records of switch malfunctions dating back to the weapon's initial deployment. Jones reviewed incident reports documenting more than 30 cases where MC-722 switches had activated without deliberate operator input. These inadvertent activations occurred during routine maintenance procedures, electrical system testing, and various emergency conditions that generated stray electrical currents within weapon systems. The switch mechanism itself consisted of a rotating solenoid assembly that controlled access to the weapon's primary arming circuits. When electrical current was applied to the solenoid coil, an internal armature would rotate 90 degrees, aligning electrical contacts that enabled power flow to downstream arming systems. The rotation required sustained electrical input. Brief voltage spikes would not provide sufficient energy to complete the switching action. However, aircraft electrical failures often produced exactly the kind of sustained current flow that could activate the mechanism. Jones discovered that weapon designers had recognized the switch's vulnerability and had developed an improved replacement system. The MC-1288 switch incorporated design modifications that prevented thermal battery charging when the weapon remained in safe position. This newer switch required higher voltage levels and included additional safeguards against inadvertent activation. However, implementation of the improved switch had proceeded slowly through the nuclear weapons inventory. Neither Mark 39 weapon that fell over Goldsboro had been equipped with the newer MC-1288 switch system. Both weapons retained the original MC-722 design, despite its documented history of malfunction. The delay in upgrading existing weapons reflected the enormous logistical challenges of modifying nuclear devices that were already deployed with operational military units worldwide. Strategic Air Command's airborne alert missions placed particular stress on nuclear weapons safety systems. B-52 aircraft carrying live nuclear weapons flew continuous 24-hour missions that exposed the weapons to extended periods of vibration, temperature variation, and electrical system cycling. These operational conditions were significantly more demanding than the controlled environments used for weapons testing and evaluation. The Chrome Dome program required Strategic Air Command to maintain multiple nuclear-armed bombers in flight at all times. Aircraft would take off from bases in the Sawai, continental United States, fly predetermined routes that brought them within striking distance of Soviet targets, then return for landing and crew rotation. This continuous operation meant that American nuclear weapons spent thousands of flight hours exposed to the mechanical and electrical stresses of long-range bomber missions. Jones examined the broader context of nuclear weapons accidents that had occurred during airborne alert operations. The Goldsboro incident was not an isolated event. Strategic Air Command had experienced multiple aircraft emergencies involving nuclear-armed bombers. Each accident presented unique challenges for weapons safety systems that had been designed primarily for controlled delivery scenarios rather than emergency conditions. Bob Purifoy, former director of weapon development at Sandia National Laboratories, provided technical perspective on the fundamental challenges of nuclear weapons safety. Purifoy explained that nuclear weapons were designed as relatively simple mechanical devices that responded predictably to specific environmental inputs. The weapons incorporated sensors that detected altitude, acceleration, and timing sequences associated with normal delivery procedures. The problem arose when emergency conditions created environmental inputs that mimicked normal weapons delivery scenarios. As Purifoy noted, nuclear weapons could not distinguish between intentional deployment and accidental separation from aircraft. The bombs would interpret rapid altitude loss, violent acceleration, and electrical system activation as indicators that nuclear detonation was required. Jones's analysis revealed that the Mark 39 weapons had performed exactly as designed during the Goldsboro accident. The weapon's environmental sensors had correctly detected the altitude and acceleration signatures associated with weapons delivery. The electrical systems had activated appropriately when aircraft power was lost and internal batteries took over. The The weapons had armed themselves because their sensors interpreted the emergency conditions as normal operational deployment. The technical investigation also examined the weapons' physical design characteristics that influenced their behavior during the accident. Each Mark 39 weapon measured 12 feet in length and weighed approximately 10,000 pounds, creating significant momentum during freefall. The weapons were designed for delivery at altitudes between 35,000 feet for freefall deployment or between 3,500 and 5,700 feet for parachute-retarded delivery. The parachute system on the Pharaoh bomb had deployed automatically when barometric sensors detected the appropriate altitude. This deployment occurred exactly as designed, demonstrating that the weapon's environmental sensing systems were functioning normally. The parachute reduced the weapon's impact velocity and prevented the violent deceleration that could have triggered additional arming mechanisms. The farmland bomb had experienced the full force of ground impact without parachute deployment. The weapon had struck soft, recently plowed earth that absorbed much of the impact energy, but the deceleration had still been sufficient to activate multiple internal systems. The ground impact had created exactly the kind of environmental conditions that the weapon's sensors interpreted as the final phase of nuclear delivery. Jones's technical analysis demonstrated that both weapons had responded appropriately to their programmed logic sequences. The safety systems had functioned as designed, but those designs had not adequately accounted for the specific combination of emergency conditions created by aircraft structural failure. The weapons had armed themselves not because of system malfunctions, but because their environmental sensors could not distinguish between intentional combat deployment and accidental separation from a disintegrating bomber. The investigation revealed fundamental assumptions in nuclear weapons design that had not been adequately tested under real-world emergency conditions. American nuclear safety protocols relied heavily on preventing accidents rather than ensuring weapon safety after accidents occurred. Jones's investigation into the Goldsboro incident led him to examine classified records documenting the broader pattern of nuclear weapons accidents that had occurred since 1945. The Defense Department's internal accident reporting system revealed that nuclear weapons safety problems extended far beyond the single incident over North Carolina. Between 1950 and 1968, military records documented at least 700 significant accidents involving 1,250 nuclear weapons. These incidents included aircraft crashes, transportation accidents, storage facility fires, and handling errors that exposed nuclear weapons to conditions their safety systems had not been designed to withstand. Each accident provided data about how weapons behaved under emergency conditions, but the information was compartmentalized within classified reporting channels that limited broader analysis of systemic safety problems. Secretary of Defense Robert McNamara had received briefings documenting more than 60 accidents involving nuclear weapons since World War II. These briefings included 2 particularly disturbing cases where nuclear-tipped anti-aircraft missiles had been launched inadvertently during peacetime operations. The accidental missile launches demonstrated that nuclear weapons safety problems were not limited to strategic bombers. They affected the entire spectrum of nuclear-armed military systems. The accident reports revealed fundamental vulnerabilities in American nuclear command and control procedures. Strategic Air Command maintained operational control over hundreds of nuclear weapons through a decentralized system that granted significant autonomy to field commanders. General Curtis LeMay, as head of Strategic Air Command, exercised direct control over nuclear-armed bombers that could reach Soviet targets within hours of receiving launch orders. This command structure meant that individual generals controlled enough nuclear firepower to initiate global nuclear war without direct authorization from civilian leadership. General Thomas Power, who succeeded LeMay as Strategic Air Command Chief, maintained similar authority over strategic nuclear forces. Defense officials worried privately about scenarios where unstable field commanders might launch nuclear attacks based on their own assessment of international situations. The NATO deployment of American nuclear weapons created additional command and control complications that violated federal law regarding nuclear weapons custody. United States nuclear weapons stationed in West Germany, Turkey, and other allied nations were subject to dual-key arrangements that gave host countries partial control over American nuclear assets. These arrangements were designed to reassure allies about their security while maintaining American oversight of nuclear weapons use. However, The practical implementation of dual-key systems created situations where Allied military personnel could potentially gain unauthorized access to American nuclear weapons. Intelligence reports indicated particular concern about the reliability of Turkish and West German personnel who had access to nuclear storage facilities and delivery systems. The political instability in these regions raised questions about whether American nuclear weapons might be seized or misused during domestic crises. The sealed pit design philosophy adopted for newer American nuclear weapons created different safety challenges. Traditional nuclear weapons maintained physical separation between fissile materials and explosive components until final arming procedures were completed. This separation provided an additional safety barrier that prevented nuclear yield even if other safety systems failed during accidents. Sealed pit weapons embedded plutonium cores directly within bomb assemblies, eliminating the separation that had provided traditional safety margins. The new design reduced the time required to prepare weapons for combat use, but it also meant that weapons were perpetually ready for nuclear detonation if their electronic safety systems failed. Any malfunction that bypassed electronic safeguards could potentially result in nuclear yield. Jones discovered that American nuclear weapons deployed overseas operated under different safety protocols than weapons stationed within the continental United States. Overseas weapons were maintained in higher states of readiness to reduce response times during potential Soviet attacks. This enhanced readiness required weapons to remain in partially armed conditions that would have been considered unacceptably dangerous for domestic operations. The geographic distribution of American nuclear weapons also complicated safety oversight. Nuclear weapons were stored at dozens of military installations throughout Europe, Asia, and the Pacific, making comprehensive safety monitoring difficult. Each storage site operated under different local conditions and security procedures that could affect weapon safety systems. Transportation of nuclear weapons between installations exposed the devices to additional accident risks. Nuclear weapons moved by truck, aircraft, and ship along routes that brought them through populated areas where accidents could have catastrophic consequences. The transportation procedures included safety protocols designed to prevent unauthorized access, but these protocols were not specifically designed to address the kinds of mechanical failures that could trigger inadvertent arming. Jones's analysis revealed that the American nuclear arsenal had grown so rapidly during the 1950s that safety systems had not kept pace with deployment schedules. Weapons designers had focused primarily on ensuring nuclear yield reliability rather than preventing accidental detonation. The urgency of Cold War nuclear competition had created pressure to deploy weapons before comprehensive safety testing could be completed. The institutional culture within nuclear weapons agencies also contributed to safety problems. Military and civilian officials responsible for nuclear weapons frequently emphasized operational readiness over safety considerations. This emphasis reflected the strategic doctrine that nuclear deterrence required weapons to be immediately available for use, creating resistance to safety measures that might reduce operational effectiveness. Nuclear weapons laboratories operated under budgetary and schedule pressures that limited the resources available for safety system development. Most research funding was allocated to improving weapon yield and reducing weapon size rather than enhancing safety mechanisms. Safety improvements were often treated as secondary priorities that could be addressed after operational requirements were met. The compartmentalized nature of nuclear weapons programs also hindered comprehensive safety analysis. Different agencies were responsible for weapon design, deployment, storage, and transportation, but no single organization had authority to examine safety issues across the entire nuclear weapons system. This organizational structure made it difficult to identify systemic safety problems that affected multiple aspects of nuclear weapons operations. Jones concluded that the Goldsboro incident represented a typical example of how American nuclear weapons behaved under emergency conditions, rather than an exceptional case of safety system failure. 3 days after John F. Kennedy's inauguration on January 20, 1961, the new president received his first detailed briefing on the Goldsboro nuclear weapons accident. The timing of the incident, occurring so early in Kennedy's presidency, forced the administration to confront nuclear safety issues that had received limited attention during the Eisenhower years. Kennedy's response would fundamentally reshape American nuclear weapons policy and accelerate the development of safety systems that had been delayed by bureaucratic inertia. Kennedy immediately ordered a comprehensive review of Strategic Air Command's airborne alert operations. The president was particularly concerned about the risks associated with keeping nuclear-armed bombers continuously airborne over American territory. The Goldsboro accident demonstrated that aircraft mechanical failures could create exactly the conditions that nuclear weapons interpreted as combat deployment scenarios. The president directed Secretary of Defense Robert McNamara to reduce the number of aircraft participating in airborne alert missions while maintaining sufficient nuclear deterrent capability. This directive required Strategic Air Command to modify its operational procedures to minimize the time that nuclear weapons spent airborne while preserving the ability to respond rapidly to Soviet aggression. Kennedy also mandated immediate installation of permissive action links on all American nuclear weapons. PAL systems were electronic devices designed to prevent nuclear weapons from detonating unless authorized personnel entered correct authorization codes. The technology had been under development since the mid-1950s, but deployment had been delayed by military resistance and technical challenges. The Lawrence Livermore National Laboratory received primary responsibility for developing PAL systems that would meet Kennedy's requirements. Livermore scientists faced the challenge of creating electronic locks that would prevent unauthorized nuclear weapons use while remaining reliable under combat conditions. The PAL systems needed to function in the harsh electromagnetic environments created by nuclear explosions while resisting tampering attempts by hostile forces. The initial PAL design incorporated a 4-digit numerical code that authorized personnel would enter using mechanical switches mounted within each nuclear weapon. The system required operators to input the correct code sequence before the weapon's arming circuits would become active. Incorrect code entries would disable the weapon permanently, preventing unauthorized use even if the device was captured by enemy forces. Livermore engineers also developed tamper resistance features that would destroy nuclear weapons if unauthorized personnel attempted to bypass PAL systems. These anti-tamper mechanisms used conventional explosives to scatter nuclear materials without creating nuclear yield, rendering stolen weapons unusable while avoiding radioactive contamination. The technical challenge of integrating PAL systems into existing nuclear weapons required extensive modifications to weapons that had been designed without electronic locks. Each weapon type required customized PAL installation that maintained the device's nuclear yield capability while adding the new safety features. The modification program would eventually encompass thousands of nuclear weapons deployed worldwide. Kennedy issued National Security Action Memorandum 160 on June 6, 1962, formally directing that all United States nuclear weapons deployed with NATO forces be equipped with permissive action links. This directive addressed the command and control vulnerabilities created by dual-key arrangements with allied nations. PAL systems would ensure that American nuclear weapons could not be used without explicit authorization from United States officials. The NATO PAL installation program faced significant diplomatic challenges. Allied nations had been assured that they would maintain some degree of control over nuclear weapons stationed on their territory. The installation of American-controlled electronic locks effectively eliminated Allied influence over nuclear weapons use, creating political tensions within the NATO alliance. Military commanders also resisted PAL implementation, arguing that electronic safety systems could malfunction during combat operations and leave nuclear weapons unusable when they were most needed. Field commanders preferred mechanical safety systems that could be overridden manually if electronic components failed. The military's resistance to PAL systems reflected broader institutional concerns about civilian interference with operational nuclear capabilities. The technical development of PAL systems revealed additional safety vulnerabilities in existing nuclear weapons. Early PAL installations on W-47 warheads used in submarine-launched ballistic missiles experienced mechanical failures that left much of the United States nuclear submarine fleet armed with defective warheads. The withdrawal wires used in these early PAL systems would break after extended storage, disabling the safety mechanisms and requiring complete warhead redesign. Kennedy's safety initiatives also addressed the organizational problems that had contributed to nuclear weapons accidents. The President established new oversight procedures that required regular safety inspections of nuclear storage facilities and transportation operations. These inspections were designed to identify safety deficiencies before they could result in accidents. The administration also modified nuclear weapons transportation procedures to reduce the risks associated with moving nuclear devices through populated areas. New transportation protocols required specialized vehicles with enhanced safety features and communication systems that maintained constant contact with military command centers. Kennedy's nuclear safety program represented the first comprehensive attempt to address the systemic problems that had been identified in nuclear weapons accident reports. The program acknowledged that nuclear weapons safety required active management rather than relying solely on the initial design features of individual weapons. The pace of PAL deployment accelerated throughout 1962 as Kennedy administration officials recognized the urgency of nuclear safety improvements. The President personally reviewed progress reports on PAL installation and frequently pressed defense officials for faster implementation schedules. By early 1962, the Kennedy administration had established the framework for a fundamental transformation of American nuclear weapons safety. The combination of reduced airborne alert operations, mandatory PAL installation, and enhanced oversight procedures represented the most significant nuclear safety initiative since the beginning of the nuclear age. The technical success of early PAL systems provided confidence that electronic safety devices could effectively prevent unauthorized nuclear weapons use while maintaining operational reliability. This confidence would prove essential as the program expanded to encompass the entire American nuclear arsenal. The military establishment's resistance to permissive action links intensified as deployment schedules accelerated throughout 1962 and 1963. Strategic Air Command officers argued that PAL systems introduced unnecessary complexity into nuclear weapons operations that had functioned effectively for more than a decade. Field commanders expressed particular concern about scenarios where PAL electronic systems might malfunction during actual combat operations, rendering nuclear weapons unusable precisely when they were most needed. General Thomas Power, who had succeeded Curtis LeMay as Strategic Air Command Chief, led institutional opposition to PAL requirements. Power argued that electronic safety devices represented an unacceptable compromise of operational readiness that could undermine America's nuclear deterrent capability. Strategic Air Command's operational doctrine emphasized rapid response times that would be degraded by additional safety procedures required for PAL activation. The military's resistance reflected deeper concerns about civilian oversight of nuclear weapons operations. PAL systems effectively transferred final authorization authority from military field commanders to civilian officials who controlled the authorization codes. This transfer represented a fundamental shift in nuclear command relationships that reduced military autonomy over nuclear weapons deployment. Technical problems with early PAL installations provided additional arguments for military opponents of the safety systems. The W-47 warhead PAL installations used mechanical withdrawal wires that were designed to disable nuclear weapons if tampering was detected. These withdrawal wires proved vulnerable to corrosion and mechanical stress that occurred during normal storage and handling operations. Submarine crews discovered that PAL withdrawal wires would break spontaneously after weapons had been stored in submarine missile compartments for extended periods. The wire failures disabled the warhead safety systems and left nuclear weapons in potentially dangerous conditions. The Navy was forced to develop new PAL designs that eliminated withdrawal wires while maintaining tamper resistance. The technical setbacks with submarine PAL systems delayed implementation schedules and reinforced military arguments that electronic safety devices were inherently unreliable. Defense officials found themselves defending PAL programs against critics who pointed to the W-47 failures as evidence that electronic safety systems created more problems than they solved. International deployment of PAL systems created additional complications that had not been fully anticipated during initial program planning. American nuclear weapons stationed in Europe operated under NATO command structures that included personnel from multiple nations. PAL installation required careful coordination with Allied military personnel who had been responsible for nuclear weapon security under previous arrangements. The 4-digit code system used in early PAL designs proved vulnerable to unauthorized access attempts by personnel, who had legitimate reasons to be near nuclear weapons. Storage facility personnel, transportation crews, and maintenance technicians could potentially observe or deduce PAL authorization codes through repeated exposure to weapons activation procedures. Technical teams at Lawrence Livermore Laboratory responded to these security concerns by developing more sophisticated PAL systems that use 6-digit and eventually 12-digit authorization codes. The longer code sequences reduce the probability that unauthorized personnel could guess correct authorization combinations, but they also increase the complexity of field operations. The expanded code systems required additional training for military personnel who would be responsible for PAL operations during combat scenarios. Training programs needed to ensure that authorized personnel could reliably enter correct codes under the stress conditions associated with nuclear weapons deployment while maintaining security procedures that prevented unauthorized access. PAL deployment schedules fell behind Kennedy administration targets as technical problems and military resistance created implementation delays. Defense officials discovered that modifying existing nuclear weapons to incorporate PAL systems required more extensive engineering changes than had been initially anticipated. Each weapon type required customized PAL integration that maintained nuclear yield characteristics while adding electronic safety features. The modification program also revealed manufacturing quality issues in nuclear weapons that had been deployed during the urgent expansion of the nuclear arsenal. In the 1950s, some weapons required complete rebuilding to meet the mechanical precision standards necessary for reliable PAL operation. Budget constraints limited the resources available for PAL installation programs. Nuclear weapons modification competed with other defense priorities for funding allocations that were already stretched by Cold War military requirements. Congressional oversight of nuclear weapons spending was limited by security classifications that prevented detailed examination of PAL program costs and schedules. The pace of PAL deployment was further complicated by the Palomares incident in January 1966, when a B-52 bomber carrying nuclear weapons collided with a refueling tanker over Spain. The accident scattered nuclear materials across Spanish farmland and created an international diplomatic crisis that highlighted continuing vulnerabilities in nuclear weapons safety. The Palomares accident occurred despite the implementation of improved safety procedures following the Goldsboro incident. 3 of the 4 nuclear weapons involved in the Spanish accident were equipped with PAL systems, but the devices still scattered plutonium contamination when their conventional explosive components detonated upon ground impact. 2 years later, the Thule incident in Greenland created another nuclear contamination crisis when a B-52 bomber crashed near an American airbase. The Thule accident demonstrated that PAL systems could prevent nuclear yield but could not eliminate the radioactive contamination risks associated with nuclear weapons accidents. These subsequent accidents reinforced arguments by PAL critics, who contended that electronic safety systems provided limited protection against the most serious consequences of nuclear weapons accidents. Military officials pointed out that radioactive contamination could create political and environmental disasters even when nuclear yield was prevented. By 1968, PAL installation had been completed on most American nuclear weapons deployed in Europe, but approximately half of the nuclear warheads remained equipped with the original 4-digit code systems. The slower than anticipated deployment meant that many nuclear weapons still operated with safety systems that provided limited protection against unauthorized use. The technical evolution of PAL systems continued throughout the late 1960s as engineers developed more sophisticated electronic locks that incorporated cryptographic principles and tamper-resistant hardware. These advanced systems provided significantly better security than early PAL designs, but their deployment would require additional years of field installation and personnel training. By 1987, a comprehensive Sandia National Laboratories review concluded that nuclear weapon safety had been fundamentally transformed since Parker Jones's analysis of the Goldsboro accident. The review acknowledged that as long as nuclear weapons remained fully assembled and deployed on combat-ready systems, there would always exist a non-zero probability of unintentional detonation. However, the probability had been reduced by several orders of magnitude through systematic implementation of multiple independent safety systems. The development of environmental sensing devices represented the most significant breakthrough in nuclear weapon safety since the original PAL systems. ESD technology incorporated sensors that detected the specific physical environments expected during legitimate nuclear weapons deployment. These sensors monitored acceleration patterns, altitude changes, and timing sequences that occurred during normal weapons delivery procedures. ESD systems required nuclear weapons to experience predetermined environmental conditions before arming sequences could begin. Weapons needed to detect the acceleration signature of aircraft release, followed by specific altitude and velocity profiles associated with ballistic trajectory or parachute descent. The environmental sensing requirements meant that weapons would not arm during transportation accidents, storage facility incidents, or unauthorized handling. The environmental sensors were designed to detect conditions that could only occur during intentional weapons deployment for military aircraft or missile systems. Ground-based accidents, even those involving high-speed impacts or explosions, would not generate the altitude and acceleration signatures required for ESD activation. This environmental discrimination provided protection against the kinds of accidents that had threatened nuclear detonation at Goldsboro. Advanced PAL systems developed during the 1970s incorporated cryptographic principles that made unauthorized code determination virtually impossible. The new systems used 12-digit authorization codes that were encrypted using algorithms developed by the National Security Agency. Authorized personnel received time-sensitive code sequences that changed according to predetermined schedules, preventing unauthorized use of previously observed codes. The cryptographic PAL systems also included anti-tamper mechanisms that would permanently disable nuclear weapons if unauthorized personnel attempted to bypass electronic locks. These mechanisms used conventional explosives to scatter nuclear materials without creating nuclear yield, rendering stolen or captured weapons completely unusable while avoiding radioactive contamination of surrounding areas. Two-man rule procedures became mandatory for all nuclear weapons operations, requiring independent authorization from 2 qualified personnel before any nuclear weapon could be armed or deployed. The two-man rule eliminated the possibility of unauthorized nuclear weapons use by individual personnel, regardless of their security clearance level or operational authority. Implementation of the two-man rule required extensive modifications to nuclear weapons storage, transportation, and deployment procedures. Military installations were redesigned to ensure that no individual could gain physical access to nuclear weapons without the presence of at least one other authorized person. Communication systems were modified to require dual authentication for nuclear weapons authorization messages. The cumulative effect of these safety improvements was measured through probabilistic risk assessment methodologies developed specifically for nuclear weapon systems. Sandia engineers calculated that the annual probability of accidental nuclear detonation had been reduced to approximately 1 in 1 million for weapons operating under normal environmental conditions. This risk level represented a 10-fold improvement over the safety margins that had existed during the Goldsboro era. Jones's original analysis of the Goldsboro incident had proven prescient in identifying fundamental flaws in nuclear weapons safety philosophy. His conclusion that the Mark 39 weapons did not possess adequate safety for airborne alert operations became the foundation for comprehensive safety system redesign that extended far beyond the specific technical problems he had documented. The institutional changes initiated by Jones's report also transformed the organizational culture surrounding nuclear weapons safety. Safety analysis became a mandatory component of nuclear weapons development programs, with independent review teams examining potential failure modes before weapons entered operational service. The compartmentalized approach that had limited safety oversight during the early Cold War period was replaced by comprehensive systems analysis that examined safety issues across all aspects of nuclear weapons operations. President Kennedy's nuclear safety initiatives had created lasting institutional momentum that continued through subsequent administrations. The safety review procedures established during the early 1960s became permanent features of American nuclear weapons policy, ensuring that safety considerations received equal priority with operational requirements. The technical success of American nuclear weapons safety systems influenced Soviet nuclear weapons development during the 1970s and 1980s. Intelligence assessments indicated that Soviet weapons designers had adopted similar environmental sensing and electronic lock technologies, reducing the global risk of accidental nuclear detonation during the final decades of the Cold War. By the mid-1980s, American nuclear weapons featured multiple independent safety systems that provided overlapping protection against accidental detonation. The weapons incorporated 12-digit cryptographic PAL systems, environmental sensing devices that required specific deployment signatures, two-man rule authorization procedures, and anti-tamper mechanisms that would destroy weapons if unauthorized access was attempted. The safety transformation also extended to nuclear weapons storage and transportation procedures. Specialized storage facilities incorporated multiple physical barriers and electronic monitoring systems that prevented unauthorized access while maintaining weapons in safe conditions. Transportation vehicles were equipped with tamper-resistant containers and communication systems that maintained constant contact with military command centers. The annual accident rate for nuclear weapons operations had dropped substantially since the implementation of comprehensive safety procedures following Kennedy's 1961 directive. The systematic approach to safety management had eliminated the kinds of cascading failures that had nearly resulted in nuclear detonation over North Carolina. In the farmland near Goldsboro, where 2 hydrogen bombs had fallen in 1961, the government maintained a permanent easement that prevented excavation near the site, where radioactive uranium from the farmland bomb remained buried in the soil. The easement served as a quiet reminder of the day when America's nuclear arsenal had been held together by luck rather than engineering, and of the engineer whose willingness to challenge official conclusions had forced a revolution in nuclear safety that made such near disasters obsolete.